Hello, everyone. My name is Michael. I'm the founder of More Than Layers, and More Than Layers is a design studio for large format additive manufacturing, or often called robotic 3D printing. I've been active in this market for more than 10 years, and I know it's quite hard to start applying this technology. There's a lot of tech involved, there's a lot of choices you have to make, and there's a lot of opportunities. So, this video should help you understand what the technology is, how to apply it, what to look for within a project, and really start to get the benefits of large format additive manufacturing. So today we will discuss. First, we will talk about AM Campus. So that's where I've been active for the last 10 years, and it's a growing club of companies with a lot of synergy around these kind of topics. We are based in Haarlem, but I will discuss it a little bit later. And then I will explain what More Than Layers is. We will touch upon machines, materials, design, and some showcases. So it's going to be packed with a lot of information. You should be able to interact with all the elements if you are watching this through Canva, and if you're watching it on YouTube, just feel free to skip ahead if it's too much into detail or you're just only interested in materials or the design part. Just skip ahead, no problem. And let's get started. So the first thing I want to discuss is the Additive Manufacturing Campus MRA. And MRA is the Metropolitan Region of Amsterdam. So this place is based in Haarlem, and it started actually in the center, in the central big hall, as a smart industry field lab for industrial additive manufacturing. And for the last 10 years, it has been growing and expanding, and startups started to pop out of it. So it became its own incubator, which More Than Layers is one of them. So one of my biggest frustrations as an application engineer in additive manufacturing is that a lot of clients came to us with a file, even SketchUp files, and the question was always, "Can you print this file?" And 9 out of 10 times, they were way too far ahead in their design process, or it was just they didn't think about the right design rules. So we had to say no 9 out of 10 times. And this frustrated me because they didn't have the right material knowledge, they didn't design with the right tooling. So I started the computational design studio to solve that boundary. We have to be involved way earlier in the design process and share that information as freely as possible so we can grow the large format additive manufacturing world. So some other companies on the terrain are, for example, Axionomic, Embrace, Neolithic, which focuses on concrete printing, Smart Makers Academy for educating your personnel into new technologies, and Baulab, which is using the same kind of production technologies, but then for the building industry. So it's actually better to just see it in a video. So I made some videos and I will talk you through it. So this is More Than Layers, and More Than Layers is a design studio. We show all the options. Everything you see except the wooden table is 3D printed. So we show you the materials, we show you the kind of design tooling we used, and we just try to inspire you and think about your next project and where you can apply it. So it's a lot of showcasing, and we also sell these objects. But the nicest way is to get inspiration from our objects and then start designing your own object. So when we designed it, it has to be produced somewhere. So that's next to us at 3D Maker Zone. 3D Maker Zone is a really big space where also events are given to stimulate the application of Industry 4.0 technologies, but at the same time, it's also a production location. So what you see here is like a lot of different kind of technologies. All the technologies are under one roof, and some robotic arms. So this is where we are going to focus on today. These are the robotic arms where most of the products of More Than Layers are printed on. It's an extruder system, which means it melts a plastic a granulate material, it melts it into layer lines, how a small 3D printer would also work, but then with really big, thick layers. So you can think of a nozzle of 4 millimeters upwards to 30, 40 millimeters. So you see some other technologies. This is, for example, a filament-based system, but still large format. It's perfect for these kind of lamps that you see in the background, and even a surfboard is printed on that. So then if we go to the back of the terrain, we start to enter the building industry. So you see some concrete prints, and you see the building lab in the background, a fully circular built building with some extra robotic arms inside. And these two robotic arms are collaborative, so one prints and the other mills. And that means that we can give a smooth surface to objects, or we can, for example, mill certain holes in it. So it creates more of a stepped approach to production. And then the last one is Neolithic. This is on the back of the terrain. And Neolithic is focused on concrete printing. Same robotic arm, just another head, another tooling with concrete. And this is built in the infrastructure sector. For example, it's printing stairs now for slopes. And in the background, you could also see some manholes. So for sewage systems, it's also a perfect solution. So if you want to watch them back, just go backwards, or you can pause it and think about it. Just do whatever you feel like, because I tend to go quite fast. So let's focus on More Than Layers. So More Than Layers is a studio. It's a design studio. So we can help you with designing spaces, with designing objects, specifically for large format additive manufacturing. So the design studio also forms a community in which we share knowledge with each other, because I really believe in the democratization of this technology. And in my world, that means activating people. Knowledge should not be the boundary of applying this technology. So we should share how we can design something. We should share how we can, what kind of materials we are using, what are the right settings for a material. So in the end, the designer can focus on designing and not on the technological aspect. If they want to innovate the manufacturing process, be my guest. Very happy to help you with that too. But most of our clients, they want to get an idea out of their head and they don't want to think about how it's produced. So we try to be the technological partner for the creative minds. So we do that, for example, for projects. So it can be interior of shops, it can be a space for a municipality, it can be a lot of different kind of settings, which we call projects. And then we also have products, which means that we have a web shop where you can buy our designs or designs of our community. So these are more furniture pieces like lamps, side tables, and you can also use them within your projects like a pick and place. But most of the time, you want to have some influence, design influence yourself, like certain kind of shape or certain kind of material. So that's also totally possible. And then those projects and products, they come together in a production network. So at the moment, in the Netherlands, we produce at 3D Maker Zone, but it would be ideal to be able to produce as locally as possible to your client. So we are setting up a production network to help with that. And this is getting more interesting day after day because the machines are getting more standardized. In the past, it was not so standardized, so every output would be a little bit different. And now we see that we really get the process under control. Brings me actually to past, present, future. So in the past, you could see there was a lot of custom made machines, so low repeatability. The designs were mainly focused on one-offs or aesthetics or outer shells. And unstandardized thermoplastics. And you see now the present is that we have more dedicated machines. So two big players are, for example, Seed and Caracol, and the install base is spread over two of those big players. So I know that if you are using a Seed, I can print in a certain kind of way, and if you're using a Caracol, I can print certain other objects. So it goes more towards parametric designs, more toolpath design, and modular elements. Fire rated is an important one, and recycled materials also. And you see that the projects focus on retail, furniture, facades, and it's going towards a more distributed hub, so more distributed production. So the early start of networks. What do we see for the future? We see more mobile print units, so a bigger install base, so we can produce more local to the client. AI is going to have a big factor in it, like it will have in every technology. I will discuss that a little bit later. It's not only the design, and designs are becoming print native, which means like it can only be produced with a robotic 3D printer. It's not it's not to replace molds. It's really its own production technology with their own characteristics. So an object with a weave pattern, it's very hard to create in another way. So if you look at materials, we are seeing more bio-based materials coming to the market, which is great, and which also helps with circularity. And the projects are gonna be more on-demand, adaptive infrastructure. So we believe that most of the warehouses will become digital. So you only produce whenever it's needed. That's a big power of additive manufacturing. And it's also a big enabler of the circular economy. Like, don't produce waste if it's not like don't produce waste at all. But how do you produce waste? That's with overproduction. So we can make sure that we never have overproduction if we produce on demand. And it's going towards a global and local federated network, full interoperability. So then you're talking about material standards and standards for the design itself. So if we look at the machines, so we are going to focus on robotic arms. Like there's a lot of different kind of machines in additive manufacturing, but today we focus on robotic 3D printing and what are the characteristics of that. So in the video we saw two different setups. On the left you see two separate robotic arms, but the difference is that one has the extruder, so the part that melts the material directly on the head, and the other one has a tube. So that means that on the first one you have um, more weight on the head, so you can move it a little bit in a different way. But the material is directly going towards the printing head, which helps with, for example, recycled materials because it doesn't degrade within the tube itself. And the second one has some more freedom on the head itself because it can turn in different ways, so it has less collision. Then on the right side, you see a multi-stage. What I already explained is like one prints, the other one mills, and you can extend that with different kind of stations. So you can think of, for example, assembling or painting. Like that's going to be the next stage in this production technology. So how does it technically work? So you have a pellet, which is like a granulate piece, just a granular plastic, which melts. It goes through different heating stages, and at the end, melted plastic comes out, and you can print layer by layer with that material. So here, for example, you see a video of one of the robotic arms with a tube, and you can see how it can go into all directions. So 3D printing, we know mainly layer by layer and just going onto one axis, but these kind of machines, they can print multi-planar, which means it can use more axes, 6-axis machines, And that means that you can print without support, for example. So it allows you to print in different ways. Then the second example is to show how we are using parametric design and algorithmic design to create structures that are normally not possible with traditional manufacturing. So here you see, for example, a coral table, which is produced with 100% recycled fishing nets and some glass fiber to keep it from shrinking. And yeah, it's really cool how you see the object get built layer by layer, and you have to think that it's produced. This table I think is around 6 hours, so it's also quite fast if you compare it to your desktop printer. So then, if we look at materials, we're going to combine materials with objects that we designed. So the first interesting material that we apply is a fiber-based material. It's using PLA combined with miscanthus, and PLA is is made from natural material as well. So this gives a really natural look and feel. It even smells like wood or fibrous material when you print it, like a little bit of burnt wood smell. It's quite nice. And we created a mirror, for example, with it. And the nice thing about this plant is that it grows close to Schiphol, which is the airport in the Netherlands, and it's used to store CO2. But it also helps prevent gooses to settle down on farmland. So Schiphol had issues with gooses going into engines, or just in general, there were a lot of gooses around Schiphol. And by growing this material, you solve that problem, you store CO2, and we can use it to print. So I really love this material. So the next one is recycled PPGF, and I will tell you what it stands for. So recycled post-consumer, which means like it's not recycled because it was a misproduction in the factory. It means it's recycled plastic after it went to a consumer. So PP means what is it? Polypropylene. I know the Dutch name, so I have to translate in my head. And GF is glass fiber. So a lot of these materials, we add a glass fiber or a natural fiber to it to make sure that the object doesn't shrink too much. Because if you heat plastic and then it cools down, you start to get internal stresses. So we call it warping, and that means that an object can bend, or you get the stress within the object, which can form cracks. So by using a fiber, glass fiber, you reduce these stresses and it shrinks less. So we made, for example, this chair with it. You can use a lot of different kind of color agents. So now it's purple, but it can be any color that you want. For example, here you see a gradient color. So we start with one material and slowly it goes towards white. This is HIPS. HIPS is high impact polystyrene, and that's made from the inside of your refrigerator. So you know that plasticky smooth material, that's HIPS. You can shred it. You can make it into a material that's printable. And also here it's 100% post-consumer recycled material. And it's very nice because it's like a smooth material, so it's easy to clean. It prints good. So also a nice material to use. Then this one is what you already saw in the video. This is the PPGF from recycled fishing nets. It's 73 to 75% fishing nets, and earlier I said 100%, because the rest is glass fiber. So the plastic material is 100% the PP, and the glass fiber is added to that. So this is one of my favorite materials and objects because it's a full story. Like it's an object inspired by nature. It looks like a coral reef. It actually is a growth algorithm. So every layer is calculated, and you really see the object grow on your screen when in your design stage. And that's translated to the robotic arm with different kind of printing layers. And the material is also very much related to the sea. So this is one of my, I would say, favorite objects. Then another material is recycled PET, and in this case, it's recycled from hospital waste. So if you, in an operation, they use a lot of one-time use plastics, for example, to put the tools in, and you cannot really um, they cannot really reuse them. So what happens is it gets thrown away, and it's chemical waste because it has blood on it, for example. So privacy is a big concern. So there's an in-between party that sources these materials. They clean it perfectly well, and they can create a super nice material out of it. Like it really looks like glass. And this was made for a side table, but you can really already see a lamp in it. So this is used a lot for lighting solutions. S is the next one. This is the same material, but then a neutral color. So we can get this one also in different kind of colors. And this is not printed with a palette, but with a filament, so with a thinner layer. Then the last material I want to discuss is PHA. This material is recently on the market, and this is 100% bio-based and biodegradable in a natural setting. So where PLA is also a bioplastic, it only uh, degrades in an industrial setting. And this material is 100% biodegradable in a natural setting, and it doesn't leave microplastics behind because it is not really a plastic. It's made from it's made by the fermentation process of bacteria in sewage water. So it converts like natural sugars into fats, and this is a material that can be made into a printing material. So we are testing. Well, we actually already printed this on a bigger scale. So now you see like a small lamp, but it's perfectly fine also to use it in a bigger scale. It just tends to warp again, but we know how to solve that. So this is a really nice material also from a bio design perspective. So talking about design for AM, what we see for the last 10 years is that a lot of designers are using CAD. So, for example, SolidWorks, Fusion, AutoCAD, very CAD based designing. And that's totally fine, of course, but it's not invented for additive manufacturing. Like CAD was invented for milling and for molds. So you're really working on surface levels. So if you are making surfaces or solids, it means that you're also going to send that surface or solid to a slicer or to a robotic arm. And that means that you can only print, for example, the outer contour of something. While we want to create designs in which we have way more control where the robotic arm goes to. So think about printing patterns, think about multi-planar printing. So CAD is okay, but it doesn't get the full potential out of 3D printing. Where you do get the full potential is in parametric design. So parametric design is more like programming an object. So you, instead of drawing a circle, you define that something is a circle, you give an input to the radius of the circle, and in that way you start building logic. So more you are building more like a pro yeah more code than really that you're drawing an object. And if you're creating code, it's in a visual way with nodes. If you're creating code, that means that you can repeat that code and you can adjust parameters, and that means that the output will change. So a parametric design means that you have one design with multiple parameters, and that uh, programmable design can lead to other designs. So if you tweak something, the output changes. So you have one object, but within that are 1,000 different variations. So that is perfect for additive manufacturing, because for the robotic arm, it doesn't matter what is printing next. It doesn't have to be exactly the same object. It can actually be totally different, as long as you thought about the the boundaries of the printing. So we use this a lot. You can generate your G code with it. So that means that you can generate how the robotic arm is gonna move, and this is a really common practice in our world. It's just not very common in the whole design world. So that's why we help companies too. Like, you have an idea in your head, you want to design something for a robotic arm for that production, and you maybe not have the parametric design skills, so we can help with that too. Then another one that's very popular is generative design. And generative design means that you define certain boundaries. You put certain forces on it. So, uh, for example, a boundary is like it has to have a steering wheel on this example left, and it has to connect to the steering axis. And in between, you can calculate what's necessary. So then it starts to create like a tree structure. It starts to calculate forces, and then the output is gonna look more or less like what you see here. And that means that you're only printing material where it's really needed. So this is something that people tend to think about if you are designing for additive manufacturing, but it doesn't work that well on a robotic arm. This is very good for powder-based printing, so metal or SLS, not so good for extrusion, because you can see that there's a lot of open structures, and what are you going to do? You cannot really print in the air, so you need to create support structures. It's just not ideal. Still super interesting, not for large format. And then the next one is yeah, we cannot skip AI nowadays. There's a lot of things happening in generating 3D models from text or from images, and that's really cool. It just doesn't mean that it's also manufacturable. So there's still a mismatch in what you create on your screen and if it will be able to be produced. So it can look super cool on your screen, and then 9 out of 10 times, again, this 9 out of 10 times, maybe now it's 99 out of 100 times, I have to tell you that you cannot just print it like that. So there are no specific tools yet that can generate only things that are gonna be produced with robotic arms. Of course, they will come. So we are focused on AI in that sense, but we just don't tend to overpromise anything. It does help to get the idea out of your head. It does help to convey a message. It does help in the initial states of the project, but it also creates a lot of extra waste that we have to get out. So I really love this quote, which is saying, I want AI to do my laundry and dishes so that I can do art and writing, not for AI to do my art and writing so that I can do my laundry and dishes. And this really brings you to the essence of, should we use AI? Where should we use AI? And how should we use AI? And I try to identify what are the laundry and dishes in additive manufacturing. So in design for additive manufacturing. And how can AI help there instead of generating designs? How can it help with all the rest, with the laundry and dishes. So what are the laundry and dishes in additive manufacturing? It's like complex mesh files. They are very big. It's hard to edit them. So a lot of people are still working in STL, which I really don't prefer. Sending files is still, yeah, not ideal. There's not a lot of interoperability in our market. So I think AI can help a lot in that sense. Post production. So we create an object, but it's not finished yet. How is AI going to help with finishing that object? And the printing parameters itself. So you see, for example, that AI build, which already has it in the name, is creating a whole platform for applying AI in the printing process itself. So this is an example of how I used AI in my design process. So on the left side, you see the design that I generated. It looked really nice from the outside, but then if you start implementing it in your production process, you start to see that, for example, it has way too steep overhangs. Some of the lines are not exactly how I want them to be, and adjusting a mesh is not ideal. So it is developing a lot. It's just not there yet. So if you design for additive manufacturing, so specifically large format, what are some things that you have to think about? So you have to think about integrating sustainability from the start. That's material choice. Like if something goes wrong with your printing process, are you able to reuse that material? Like, can you shred it again? Can you use it again? Like, keep that in mind because it doesn't go good 100% of the times. So if you want to design a bigger object, think about modular designs. So think about how you're going to assemble multiple parts together into one big part. And you can also print already certain kind of elements that help you with the assembling stage or the aligning stage. So the next lesson is think in toolpaths, not just in geometry. And what that means is like if you just design the outer shell, you will not be able to create this structure like you see on this object. Like this object, the design is really just a G code that defines where the robotic arm is going to move to. So design how the robotic arm is going to move. Don't design the object itself. The fourth one is allow for increased tolerances. Like some objects are going to be a little bit bigger, some objects going to be a little bit smaller. It really depends on the printing parameters. With these kind of big objects, you cannot expect them to be um, with a tolerance of a millimeter or less. So keep that in mind in your design stage. Moreover, this is a very obvious one, but people sometimes forget. Match the wall thickness to the nozzle size, and that means like if you're designing something and it has to connect to parts, make sure that one part is not touching the other part because you're gonna have a printing nozzle that's gonna overflow on the line that is gonna print. So if you want to have two elements that touch, be aware that you are using a nozzle of, for example, 6 millimeters or 8 millimeters, and then also design with that in mind. So if you're gonna design everywhere with a thickness of 8 millimeters, you know where it's gonna touch, and you don't want them to overlap because that creates issues with printing. Also, optimize print orientation and overhangs. So you will have a lot of issues if you design something and it has a really big overhang, which means like you are printing and it just starts to print more in the air. So an overhang is like an angle. Try to keep them below 60, 45 degrees ideally. But if you go above, you have to make sure that your tooling head is gonna move too. So 3D Maker Zone did some tests where they print with 90-degree angle, but then they created a certain structure that holds everything together. So, and manage thermal stress and warping. So, for example, all these extra elements on the down part of the design is to make sure that it doesn't start to warp and move during the printing process. So that also has to be part of your design already. There's many more lessons on how to design for a robotic arm, so for large format 3D printing. I will redirect you to this article, which is on all3DP. I wrote an article with all the details that you will need, but that is a little bit too much for this video. Then, what will be the next steps in designing for additive manufacturing? Like, where does AI come in? So what we see is that the old process is parametric, which means input parameters and it creates an output solution. In this case, a G code, so how the robot is going to move. These input parameters are going to change and it's going to be extended. So it can be generated by ChatGPT, like who is defining how a G code should be, but it's through a parametric model. It can be based on a point cloud, it can be based on a generated image, but in the end, it has to be translated to G code or robotic code. So you see that the process is changing, the input of files and file formats is changing, and it's gonna, of course, make it's gonna it's going to create a lot of extra files and a lot of extra freedom. But if you don't have the process in order, it's not going to be producible. So, what is the business case of additive manufacturing? So, we can create more personalized products. So, every object can be different. If you use a parametric design, you can add someone's name in it, for example, or a certain kind of logo or a certain kind of preferred structure. And it reduces the cost of one-offs, especially for big elements. If you have to create a really big picnic table and you first have to create a mold for it, then it's already going to be extremely expensive. In that case, 3D printing is already a very logical use case. Uh, so it can lead to faster production and lead times. This is this can be true, but you need to make sure that you already have the production capacity available, because if you produce it at someone else, they also have a backlog. So in the end, it can also take 4 to 8 weeks before your object is printed, although it can be printed within 24 hours. They tend to ask a premium fee for those kind of services. So don't send your file if you need it the next week, or be willing to pay for it. So for full circularity by design, that means like we offer to take back the elements that we sold because we know which material it's made of and we can reuse it in another object. So we can shred it, we can reuse it, we print a new object, and then we can take that back too. You cannot do this indefinitely, because material tends to degrade every time you shred it. But you can do that for 10 cycles for sure. And you can also add some virgin material to it to help with that. And there are some processes called chemical recycling, which don't tend to have that issue. And then local production is a really nice use case. You can produce as locally to your client as possible. So you don't have to produce things in China. You can print it ideally in the same city. Some showcases. So this is a showcase of a G-Star shop in which we printed the lights. Another company, Signwise, did the internal lighting systems, but it became like one object, like one project, which is very nice to start integrating other elements within your 3D printed part. Here you see another image. So it can really help. Uh, it can really help in defining some cool lights in your room. Then another showcase is a 3D printed lounge sofa. This was for a nightclub in Haarlem, and this is fully circular design. So we can reuse it 100%. We didn't use any elements that are non-recyclable. So, and it's parametrically designed, which means that we have 1,000 different kind of iterations of this sofa. So if your room is different, we can adjust it a little bit, and then it creates a different kind of setting. And while keeping in mind that it can be produced. So the other showcase is for Maison Garments, which are some pedestrals, also fully circular. Here you can see that it's using more non-planar printing paths and a gradient. Um, Super cool too. And this is a showcase to show that you don't have to only fixate on the fully printed part. You can also do some surface treatments. This is, for example, with a cork spray. So we call it the bitterball at work, which is a Dutch savory treat, and it has the structure of that. And you can see you can create like a watertight surface. You can create a soft surface. It can even be sprayed with old fabrics. So you can start to combine a plastic part or a additive manufactured part with surface treatments. And then this last one is a really big desk that was produced in multiple elements. So you can also go way bigger than only one print. You can start assembling parts and really create cool objects. Then the dodos, the do's and don'ts. So we learned the last 10 years by also failing, of course, and that's totally fine. But I want you guys to not fail, or at least don't make the same mistakes that we already did. Like, the printer is not to blame, it's more the mistakes that we make along the way. So, one thing that I already said, like printing time is not the same as lead time. Like you can plan ahead and say like, okay, it can be produced in 8 hours, so we only have to order it 1 week before. That's just not how it works. The manufacturing company is going to have a backlog, so keep that in mind. Reserve some production time. Also know that it can fail. So that's up to the production company, of course, but it can extend the lead time. So be realistic in that. You have no idea how many times I get clients that really need something within 2 days, and the design is not even ready yet. Don't give yourself that stress. It's just not needed. In most cases, it's not needed. Just be aware. And the other thing is, don't expect every print to be perfect the first time. It's a developing process. The quality is really good nowadays, but sometimes you will have some printing mistakes. Like in a lot of cases, it's not that big of an issue. If you really need to have the perfect object, you have to tweak your process because every object is unique. So every object prints differently. You can have certain parameters within boundaries, but that doesn't mean that your crazy lamp shape kind of thing can be printed with the overhang that you had in mind. You may have to start finding the boundaries. We are totally fine on finding the boundaries. And don't listen to anyone that's working in SketchUp. That's the last don't. And the do's: learn by doing. Just start using this technology. I see a lot of companies that tend to start discussing about it, like where's the use case, where's the business case. You will not find your one business case within the million possible objects that you can produce with this technology. You will find it after you did your first project, your second project, your third project. then is where you're going to recognize where the strength is specifically for your company. One example is, for example, that you can print for infrastructure, you can print manholes. The manhole is maybe expensive to print, but if the process is going to be shortened by 90%, so there's less people involved, the road has to be open for a less amount of time, like the pricing of the whole process is going to be way more in the old system than only the 3D printed part. So those kind of things you start to recognize after you're working with it. So the second do is include design for AM as early as possible, in the earliest way possible, because you have to design with certain rules, within certain boundaries, with certain materials. So don't do that as a last step. Like, we can help you from the start, and please allow us to help you from the start, because then the project tends to get better. We get clients that already have knowledge about additive manufacturing, but it tends to be knowledge from 5 years ago. So we know the latest developments and how to design for the latest developments. And that's where you're going to create unique pieces, not just copying an outer contour. That's not what makes us happy anymore. So that's the biggest lesson. Include design for AM as early as possible. Then this is a quick cheat sheet. After this one, I will end, but this is just for you to check. Just when do you use additive manufacturing? Like, is the geometry complex? What is the size of it? What is the batch size, and what does the performance has to be? So I want to thank you very much for listening. I'm not sure if you listened all the way through, but at least that you listened to some parts of it. And I hope this helps you a lot with applying additive manufacturing within your projects. And if you have some more questions, just be happy to contact me. I can share a lot of more information, specific information for your project, and we are happy to help. Thank you for listening.